Hi, my name is Aman, and we have decided to create an under and over voltage protection system for our electrical project. So we noticed that this problem of voltages going beyond threshold levels have affected motors, power supplies, and electronics. So our goal was simple. We made an analog system that automatically cuts off the load the moment the mains falls below a safe level.
Hi, I'm Prakash. I'm going to be explaining how it works. Our input supply goes through six stages in our system. First, a transformer, rectifier, filter, comparator, transistor, and finally, a relay. We are going to use these key components in our system. First, a 12012 step-down transformer and two rectifier for our rectifications. And for filtering, we're using a couple of RC circuits. And for voltage dividers, we're using 20 kilo ohm, 10 kilo ohm resistors. And we're using LM311 comparator, voltage comparator module for our comparator. And for buffering and switching stages, we're using a TIP122 transistor and a relay module. This is our prototype.
Hello, my name is Shrey, and I am going to explain the rectification and smoothing part. For our voltage protection system, we first convert AC mains to a safe DC level. We use a center tip transformer to step down the voltage to 12 RMS. This provides two AC line waves that are 180-degree out of phase relative to the center ground. To rectify this, we use two diodes to clip the negative cycles of both waves. Since the signals are inverted, combining them fills the gap, creating a full wave rectified DC signal. This doubles the pulse frequency, making it much easier to smooth. We then add a shunt capacitor to filter these pulses. However, the capacitor charges to the peak voltage, roughly 12 root 2, giving us an output of 18 volt. This higher voltage caused the capacitor to heat up, so we had to select a component with a higher voltage rating to ensure long-term reliability. Finally, we integrated a bleed resistor for safety. We faced off a trade-off. A lower resistance allows for a fast, safe discharge but introduces high voltage ripples. Conversely, a higher resistance stabilizes the DC signal but takes too long to discharge. We had to balance this to ensure the circuit remains responsive during a fault. This 18-volt filtered output now serves as the input for our comparator and under voltage detection logic.
Now, moving to the detection logic. Our system requires a stable reference to identify over and under voltage faults. We established a separate 12-volt reference rail by tapping into the Arduino Uno's power jack. Using precision voltage dividers, we stepped both the 18-volt rectified signal and this 12-volt rail down to comparable logic. These signals are fed into an LM311 comparator. The 12-volt logical reference acts as our threshold. If the rectified voltage deviates from this preset window, the comparator is triggered. When a fault is detected, the LM311 should output a full VCC signal to drive the base of our switching transistor. A major technical challenge we faced involved the specific architecture of the LM311. Based on our previous experience with the LM741 in the lab, we expected a standard push-pull output. However, the LM311 uses an open collector output. Initially, we received no voltage at the output because the pin was simply floating. Once we identified this, we implemented a pull-up resistor to the 12-volt rail, which successfully allowed the comparator to pull high and trigger the transistor. With the output resolved, the transistor now receives a clean signal to switch the relay, effectively isolating the load during a voltage fault. This ensures our protection system is both fast and reliable.
Once the LM311 triggers, the signal reaches the base of our TIP122 transistor. We have configured the transistor with the emitter grounded and the collector connected to the relay's ground terminal. When the transistor channel opens, it completes the circuit, allowing the current to flow from 12-volt rail through the relay coil. The relay acts as our physical isolation barrier. In an over or under voltage event, the mechanical switch inside the relay trips instantly, disconnecting the load from the power source. This ensures that the downstream equipment is never exposed to unsafe voltage levels. The primary challenge in this stage was signal noise. Our filtering stage left a peak-to-peak ripple of 400 millivolts, while negligible at 18 volt scale. This ripple became highly prominent at our 3 to 4 voltage logic levels. This caused the relay to flicker rapidly during the transition states as the signal hovered near the threshold. To stabilize the system, we integrated an additional filtering capacitor at the comparator output. This smoothens the triggering signal, eliminated the flickering, and ensured a clean switch for the relay. This is our project demonstration. When the rectifier voltage crosses uh, the voltage of the threshold, it's going to turn on this specific relay. And when we decrease the rectifier voltage down, like comparable to the threshold voltage, it's going to turn this relay on. The resistance of this potentiometer it will directly affect the logical voltages of both the op amps, while the inverting terminal for the under voltage and the non-inverting terminal for the over voltage. As we can see, when the rectifier went below the threshold voltage, it turned on this specific relay, which eventually cuts off the load, whatever that's connected at this end. So this is our final project demonstration.